Good evening, everyone. Today we are discussing the different methods of analysis of pre-stressing force. In that first one, where we are discussing about stress concept. In stress concept, the main thing we are concentrating on the calculation of stresses developing due to pre-stressing force and stresses developing due to dead load and live load. In this concept, we are considering all the effects of pre-stressing force as well as dead load and live load. Here we have two different cases, concentric pre-stressing and eccentric pre-stressing. As the name itself indicates, in concentric pre-stressing, the tendon will be provided along the neutral axis or centroidal axis of the section. When the tendon is provided along the neutral axis or centroidal axis, the pre-stressing force will develop the direct compressive stresses on the concrete, but there will be no bending stresses in the concrete. And in addition with pre-stressing force, we are going to consider bending stress due to dead load and live load. The diagram indicates the direct stress, that is P by A, due to pre-stressing force, and bending stress due to dead load and live load. And the last third diagram is resultant stress. Next case is eccentric pre-stressing. Here the location of the tendon is provided below the centroidal axis or neutral axis of the section. In this case, along with direct compressive stress developed by the pre-stressing force and bending stress due to dead load and live load, since we have eccentricity, the bending stress due to pre-stressing force also develops. So, in addition with direct stress due to pre-stressing force and bending stress due to dead load and live load, we also consider bending stress due to pre-stressing force. This is stress concept. In stress concept, we are going to calculate the stresses likely pre-stressing force, that is direct stress and bending stress due to dead load and live load. So the problems what we have solved in previous classes, those problems itself come under stress concept, that is calculation of fiber stresses in top of the section and bottom of the section, that is FT and FB. You have formula on the screen. Next concept is force concept. It is also called as thrust concept or internal resisting couple. In force concept or thrust concept, as we know, we are applying the tensile stresses or tensile forces on the tendons or a steel cable what we are providing for the application of pre-stressing force. After casting and the concrete get hardens, as we know, the steel, when you release the steel after applying the tensile stress, it will try to come back to its original position. During that time, in hardened concrete, the same tensile stress or tensile force in the steel or in the tendon is in turn apply the compressive force on the concrete member or on the concrete. So that compressive force or compressive stresses will be exactly acting at the location at the tendon where you have provided. That is when you have considered only pre-stressing force in the member. That is, we are not considering dead load and live load. After consideration of dead load and live load, As the load increases, the compressive force gradually shifts upwards from the location of the tendon. That shifting of the compressive force above the tendon indicates that we are applying the load and we are transferring the tensile stresses from the steel to compressive stresses from on the concrete. As we know, if you consider only pre-stressing force, top fibers will be under tension and bottom fibers will be under compression. When you apply the loads, either it may be dead load or live load, the tension zone from the top and compression zone from the bottom will gradually shifts reverse. That is, compressive zone gradually shift towards upwards and tension zone gradually shift towards downwards. So in this situation, the distance between the tendon and the maximum compressive stress level above the tendon is called as lever arm. That is, distance of the compressive stress and tendon. Then here we have stress distribution diagrams with the different cases. So first figure indicates the compressive stress is exactly acting at the location of the tendon, that is before consideration of pre-stressing force, dead load and live load. In second figure we can observe, when we have considered dead load and live load, the compressive stress is gradually shifts upwards, that is C. So that lever arm, the distance between tensile stress or position of the tendon and compressive stress is called lever arm. That is calculated by using the formula md plus ml by p. md and ml are moment of dead load and live load, and p is pre-stressing force. E dash is nothing but it is the distance between the centroid of the section to the compressive force. So the total eccentricity minus lever arm, we will get the position of the compressive force from the centroid. So that we will consider as eccentricity, and with respect to that eccentricity we have two conditions. If E dash is positive, then bottom fibers will be under compression and top fibers will be under tension. That is, compression zone is not yet shifted above the tendon location. If E dash is negative, then bottom fibers will be under tension and top fibers will be under compression. That is, compression zone is shifted above the tendons. So for calculation of fiber stresses at top and bottom for two different cases, we have formulas FT and FB shown on the screen. Next concept, and it is more important concept, it is load balancing concept. In this concept, the name itself indicates we are balancing the load. As we know, pre-stressing force leads to upward deflection of the member, and dead load and live load leads to downward deflection of the member. So that is nothing but pre-stressing force is acting in upward direction and dead load and live loads are acting in downward direction. For example, if we are applying pre-stressing force of 100 kilonewtons, that 100 kilonewton is acting in upward direction, then we gradually apply the dead load and live load. If we consider the total dead load and live load will be about 150 kilonewton, then we need to balance pre-stressing force and dead load and live load. So here 100 kilonewton will be pre-stressing force and 150 kilonewton will be dead load and live load. By using this concept, we are going to design the section for the extra amount of 50 kilonewton, that is 100 kilonewton of pre-stressing force is balancing the 100 kilonewton of dead load and live load. Additional 50 kilonewton will be considered for the provision of or for the design of pre-stressing member. So for that, we need to consider the bending moment due to dead load and live load as well as bending moment due to pre-stressing force. How to calculate? What is the bending moment due to pre-stressing force? That is pre-stressing force into eccentricity divided by WLP, that is 8 PE star by L square. If you observe the figure, see here we have formula M equals W dash by L square by 8. So W dash is in the example what I have told, 100 kilonewton of pre-stressing force and 150 kilonewton of dead load and live load. That 50 kilonewton what excess load we are applying, that will be your W dash. For that you are considering the moment and you are going to calculate the fiber stresses. That sigma T and sigma B, it is same as Ft and Fb. Since we are considering as the stresses, it can be denoted by both F or sigma T and sigma B. Here I have considered parabolic profile of the cable. E star indicates the total dip of the cable. In first figure, the eccentricity at support is 0 and eccentricity at midspan we have E star. But in second case, we have eccentricity at both support as well as midspan. At supports, we have eccentricity above the neutral axis or centroidal axis, and at midspan, we have eccentricity below the centroidal axis. So we have two eccentricities, one below the centroidal axis and one above the centroidal axis. But E star is total depth of the or total dip of the cable. So for those two cases, we can use the formulas, and for calculation of moment we have formula in the last page. So here we have one more case when we have providing the cable with straight cable with the angle at the midspan, or in visually we can say it as triangular profile. In this case we have two different parameters. So to balance the load, the net downward load we need to calculate. W is the total dead load and live load, and 2P tan theta, it is a component of the P or component of pre-stressing force, and for that W dash L by 4, it is, since we are using point load, that will be moment of point load. WDL square by 8, it is UDL, that is dead load, WL square by 8. So here we don't have eccentricity at supports, so directly we are calculating Ft and Fb. In case 2, we have eccentricity at support as well as eccentricity at midspan. So there we have additional parameter for calculation of moment M value, that is we are considering the moment above the neutral axis, that is P into E2. This is about load balancing concept. The last topic of the first module, we have pressure line. Here, if you recall the thrust concept, we have considered tensile force or tensile stresses in the tendon and compressive force in the concrete section. As I said, when you release the tendon will be under tensile stress, and the same tensile stress will in turn act or in turn apply the compressive force on the concrete. So when we consider only pre-stressing force acting in the member, both tensile stress and in the tendon and compressive stress in the concrete will be at the same level. When you consider or when you applied the dead loads and live loads on the member, then your compressive force gradually shifts upward from the level of tensile stresses. That is, from the tendon level, your compressive stress gradually shifts upwards. So the distance between tendon and compressive force at any section is called as lever arm, and the line joining the points of compressive stress along the sections at any sections is called pressure line. The amount of lever arm is calculated by using bending moment due to dead load and live load, and it depends upon length of the member, that is span. So in figure you can observe P is the pre-stressing force. Before applying W, that is dead load and live load, the compressive force will be act at the level of P only. But when you apply W, that is dead load and live load, you get the curve like this. That point 1, 2, 3, 4, 5, we have different points. At each point we will be having two different lever arms. So in third figure you can observe the distance between tendon and the position of compressive force is called lever arm, and the curve which is indicated there above the tendon level is called pressure line. So for calculation of lever arm at any point is the ratio of bending moment due to dead load and live load at that point or at that section to the pre-stressing force. M1 is nothing but we have considering the bending moment at section 1 and it is divided by pre-stressing force. What is the significance of pressure line? Why it is necessary? So this pressure line is very important in deciding the position of the tendon. Based on the pressure line, we can decide the position of the tendons. So the deflection of the member, what is the load carrying capacity of the member is purely depend on the position of the pressure line, and any change in bending moment in the PSC member which occurs, it will causes the shifting of pressure line. So when you increase the load, obviously the bending moment due to load will increases. As the bending moment due to load increases, the pressure line shifts again upwards or downwards. When it is increased, it should go upwards. So this is about pressure line, which is one more important topic. So here we have few examples to calculate the location of the pressure line. So in that first example, a pre-stressed concrete beam with a rectangular section of 120 mm wide and 300 mm deep supports a UDL of 4 kN per meter which includes self weight of the beam. The effective span of the beam is 6 meter. The beam is concentrically pre-stressed by a cable carrying a force of 180 kilonewton. Locate the position of pressure line in the beam. So here we have cross section of the beam of 120 mm upon 300 mm, and UDL of 4 kilonewton per meter is acting, which includes the dead load of the beam, that is 4 kilonewton is inclusive of self weight as well as live load, and the beam is of a span 6 meter, and the concentrical pre-stressing is done with a force of 180 kilonewton. We need to calculate, or we need to find out what is the position of the pressure line. So first we have considered the beam. We have to find out the support reactions. Why it is necessary means, why support reactions we have to calculate means, so to know the approximate profile of the pressure line, we need different sections, at least some 3 to 4 points we need to locate. Based on that we can draw the curve. So at midspan we have WL square by 8. At midspan moment we can easily calculate for UDL. So at different sections, so here we have considered quarter span on either side, that is the span is 6 meter, quarter span means 1.5 meter on either side, either supports, from either supports. So to calculate the bending moment at quarter span we need support reactions, so we have calculated here. At midspan we have WL square by 8, and at quarter span we have calculated here. So for the given load, midspan moment is 18 kilonewton per meter and quarter span moment is 13.5 kilonewton meter. So what is the position of pressure line? Here we have only calculated the bending moments. Now we need to calculate lever arm at different positions or different points. So shift of resultant compressive force from the position of the tendon at quarter span, that is at 1.5 meter. So moment at M1 or M2 you can observe here at point 1 or at point 2, both we have considered at quarter span or 1/4 of the span from either support. So we have M1 and M2 divided by pre-stressing force, we have got 75 mm. Same way at midspan we have M by P. We have calculated 18 kilonewton meter divided by 180 pre-stressing force. So this is the section of depth 300 mm, and if you take centroid it is 150, and concentrically pre-stressed member. So pre-stressing force or tendon is placed along the centroidal axis. At quarter span we have lever arm of 75, and at midspan we have lever arm of 100 mm. So by joining those points we can get the pressure line. This is simple problem. This is one way of solving the problem. And another method, in next example, a rectangular concrete beam 250 mm wide and 300 mm deep is pre-stressed by a force of 540 kilonewton at a constant eccentricity of 60 mm. The beam supports a concentrated load of 68 kilonewton at the center of the span of 3 meter. Determine the location of the pressure line at the center, quarter span and support sections of the beam. Neglect the self weight of the beam. So here in this question the cross section of 250 by 300 mm is given, and pre-stressing force of 540 kilonewton is eccentric pre-stressing with an eccentricity of 60 mm below the centroidal axis. The beam supporting a concentrated load of 68 kilonewton at midspan. So the total span of the beam is 3 meter, and it is supporting a point load or concentrated load of 68 kilonewton exactly at the center. You need to find out what is the location of pressure line at midspan, quarter span and support sections. Since we are neglecting the self weight of the beam, no need to worry about it. So In this problem I have solved a problem with different method by considering stresses, fiber stresses we have calculated here. So usually for calculation of fiber stresses we need area of the member, moment of inertia, then centroidal distances, sectional modulus, everything we have calculated here. Then since we are not having dead load, directly we have calculated moment for live load, that is WL by 4 since it is point load. Then FT and FB, top fiber stresses and bottom fiber stresses have calculated. Then here the fiber stresses what we have calculated, it is exactly for the center of the span, that is we are locating the calculating the lever arm for the mid span, that is pressure line, location of pressure line at mid span. So taking moments of area about the top, first we need to draw the resultant stress distribution diagram, and we need to locate the centroid of that particular stress distribution diagram. At bottom we have 2.17 Newton per mm square, and at top we have 12.22 Newton per mm square. So this is trapezoid. We need to split this section into rectangle and triangle. So same, we need to find out the centroid by calculating centroidal distance. We will get 115.08 mm. Remember, this is taking with respect to top. In next case, the same thing we need to calculate with respect to quarter span. So total span is 3 meter, quarter is, that is 1.14 of the span, means 0.75 meters. So 68 kilonewton only load acting at the mid span. So support reaction will be 34 kilonewton. Bending moment at quarter span we need to calculate. We have got 25.5 kilonewton meter. By using that moment we need to find out again fiber stresses at the top and bottom. Further, again we need to draw the stress distribution diagrams. At top fiber we have 5.33 Newton per mm square, and at bottom we have 9.06 Newton per mm square. So again moment of area about the top. Remember, we are calculating the centroidal distance from the top. Again it is trapezoid shape, split into rectangle and triangle. Calculate the centroidal distance from the top. We have got 162.9 mm. So if you observe the figure, the values what we have calculated for, that is centroid of the stress distribution diagrams, resultant stress distribution diagrams, are from the top. We have total depth of the section of 300 mm and eccentricity of 60 mm. So from top fiber we have 210 mm to the tendon, or location of P is 210 mm from the topmost fiber or top of the beam, and the Y values what we have calculated is from the top. But what we call as lever arm, it is the distance from the tendon to the location of the compressive force. So 162.9 it is from the top. So the remaining distance, it is 210 minus 162.9, we will get 47.1, that is the lever arm. 47.1 is the lever arm. Similarly at mid span, 210 minus 115.08, we will get 94.92. Here 94.92 is the lever arm. By joining those curves, those points, we got the pressure line. This is another method of calculation of pressure line. So in these two methods, one is directly considering the moment as in first problem, and calculation of lever arm by using M by P formula, or second method by calculating the fiber stresses based on the marks. If the problem is asked for about 4 to 5 marks, you can go with first method only, as same as in case of first problem. If it is asked for more than 5 marks, better you solve it with calculating the fiber stresses. So this is about your first module. Thank you.